Hello everyone, my name is Devin Hunter and today I want to talk to you all about my implementation of the ROS Navigation Stack on a real-time differential drive robot. Now before I go deeper into how exactly I went about implementing the ROS Navigation Stack, I deemed that it was appropriate for me to first explain what exactly is a differential drive robot. And for those who do not know, at its most basic definition, a differential drive robot is one whose motion, the linear and angular components, is dictated solely by the wheel velocities on the left and right side of the robot. And this can be clearly shown within this diagram that I got right here, where it has three different scenarios of the same differential drive robot. As you can see, it has wheels on both its left side and right side. In the first scenario, you have the left wheel and right wheel spinning at the same speed. So that essentially means that the robot is going to move straight with no spinning component. For the next component, you see that the right side is moving a little bit faster than the left side of the wheels. So that's causing the robot to actually turn a little bit to the left as it's moving forward. And in this last case, you see that the right wheel is moving forward while the left wheel is moving back, which is essentially causing the robot to rotate in place at double the angular velocity that it would with just one wheel. And all of this is going to be important, as this is the basis for the kinematic model that I'm going to use when I'm going about the actual implementation of navigation algorithm, amongst other things. So, moving on to the layout of the design differential drive robot, we can see that the robot is equipped with multiple different sensors, among other devices, that will allow for the robot to be able to achieve autonomous navigation, amongst other capabilities. We can see that it is equipped with the LD14 LiDAR sensor, a Raspberry Pi 4, an Intel RealSense D435 RGBD camera sensor, infrared wheel encoders, a 6 degree of freedom IMU or inertial measurement unit sensor, L298N H-bridge motor controller, and all of these devices are being controlled by the Arduino Mega microcontrollers, and the microcontrollers themselves are actually being controlled by the Raspberry Pi. The robot is also only being powered by about 16 volts approximately at any given time. Moving to here, I just wanted to talk a little bit more about the actual connection interfaces that the robot uses in order to be able to operate in the way that it does. So as you can see here, the robot utilizes the Robot Operating System, or ROS, framework and its related Arduino packages to communicate sensor data, among other things, from the robot to a remote computer and vice versa. And so I've created a small little diagram here which basically describes that this ROS framework that we don't know too much about is essentially sending data, amongst other things, to the two Arduinos on board the robot, and those Arduinos are sending data, among other things, back to the ROS framework through this interface called ROS Serial. And also, as a quick note, both the robot and the remote computer that I was utilizing in the study are using the noetic distribution of ROS, which is basically just another version that is being used of ROS. So I'm sure there are some of us who are wondering, what exactly is ROS, or this Robot Operating System framework? And below I put together a small and quick demonstration of showing how exactly ROS works by having a remote computer sending velocity commands to the robot via teleoperation. And for those who do not understand, teleoperation is basically human user input, so I'm essentially sending velocity commands to the robot via my computer. And so we have this teleop publisher, which basically sends the velocity commands to this topic called bell command, which this node right here called serial node is subscribed to this bell command to receive velocity messages. So essentially what you see here is this teleop publisher sending velocity commands through this topic, and the topic is publishing those messages to the serial node, which essentially is sending those velocity commands from the computer to my robot in real time. And we can see right here that these robots, the robot and the remote computer, are able to connect and talk with each other via their IP addresses. So moving forward, I feel like it would be a good idea to talk a little bit more about the kinematics of the design robot that I'm using in this study. So based off of the motion that I've observed from the robot, I've determined that it would be best to assign a differential drive kinematic model to it. And we can see in this image in the bottom left that we have a differential drive robot that is equipped with 2 wheels, and it has 2 frames of reference that it's using. So it has a static inertial frame, XY and YI, then also has a body attached frame, which is XR and YR. And we can see that in this first matrix equation, that's titled the forward kinematic differential equations, we can relate the global state variables of x dot, y dot, and theta dot to the local wheel velocities on the robot, theta dot r and theta dot l, which basically represent the wheel velocities on the left and right side of the wheels. Through this matrix equation, we could determine that. And we can also determine the local linear and angular velocity of the robot based off of the wheel velocities on both the left and right side. And both of these equations will be very important moving forward as they help with odometry estimation, which basically tracks the position and velocity of the robot in real time. So moving forward, now that we have talked about how exactly the robot goes about operating and going a little bit into the kinematics of the robot, we can now talk about the required steps needed for the robot to achieve autonomous navigation. And the first and arguably most important aspect of that is to find a way of accurately and robustly tracking the position and velocity of the robot at any given point in time. And that is where the ROS robot localization package comes in handy. The ROS robot localization package contains common filter algorithms for both the extended common filter and the unscented common filter. For this study, I decided to use the extended common filter algorithm, and we can see for this picture on the left is basically some pseudocode of the extended common filter where you have a prediction step and a correction step. And the prediction step is basically the algorithm predicting where the robot potentially is, and then based off of sensor measurements, there's a correction step where basically it fixes that prediction to find the most optimal state estimate of where the robot could be. And on the right side, this image right here basically represents some pseudocode of the extended common filter in action from the robot localization package. And the important part that I want you guys to notice is the twist 0 config and the IMU 0 config parameters. And basically what these do, they tell the extended common filter algorithm to determine what parts of each sensor message it should incorporate into its state estimate. And so, for example, for this twist 0 config, this basically represents the configuration for the measurements coming from the wheel encoders. And as you guys can see right here, I only wanted to give back linear velocity measurements on both the x and y direction. And then in the IMU configuration, I wanted to send back angular velocity and angular position commands in the z direction. So the yaw angular position and the yaw angular velocity. So now I want to show you all a quick demonstration of the robot moving around in space while the extended common filter algorithm estimates the robot's position and dynamics in real time. And we can see that the algorithm is able to track the robot's linear and angular position pretty well. And I know you all noticed a purple circle around the state estimate, and essentially what that represents is the pose covariance that is growing without bound. And the reason why it's growing without bound is because there is no global state estimate, such as something from a GPS or something of that nature being fused into the extended common filter algorithm to like converge the pose estimate. And because of that, that's something else that I can improve in the design of the robot moving forward. So now, moving on to the second integral step of achieving autonomous navigation, we have to understand simultaneous localization and mapping, or SLAM. And SLAM, simply put, is the use of onboard sensors to construct and update a map that represents an environment that has not yet been explored by the robot. And this can be seen in this bottom left GIF where we have this small robot moving around in a virtual space with an attached LiDAR sensor, where it's essentially able to determine what areas are free space and what areas have obstacles in front of it. And we can see that the walls, along with these small little cylinder pieces, all represent different obstacles. We can see these white dots, they all represent obstacles along with the walls. And moving to this image on my right, I actually have a mapped out environment that was built by the robot of my workspace that I was essentially able to use using a SLAM algorithm that will go into further detail in the next couple slides. And now we can move on to the SLAM algorithm utilized by the robot, which in this case was real-time appearance-based mapping, or RTAB map. Real-time appearance-based mapping is a visual SLAM graph-based approach based on incremental appearance-based loop closure detection. And for those who do not understand what incremental appearance-based loop closure detection is, you can think of a small robot that has a camera attached to it. And this camera is essentially able to process many images over time. We can look at one image that the camera is processing and say that it's able to distinguish multiple parts of whatever is within the image. So for example, we could say that the image contains a chair or a table, anything that's not uniformly shaped like a wall or anything like that. Essentially, it's able to distinguish parts of that image that make it distinguishable. And we could look at another image in the future, and it may also possess some of those same distinguishable features. And essentially what this loop closure algorithm is going to be able to do is look at both of those images and say, wait a second, both of these images have a lot of the same distinguishable features. And so it's going to make up the hypothesis that they're within the same location of each other. And then from there, once that hypothesis is accepted, a map constraint is added and these locations are essentially combined with each other. And we can look at these two images right here, where we can see from this image on the right that as the robot or whatever was possessing the camera was moving around, it was able to produce many different loop closure detections because it was able to look at many different features within the map and say, wait a second, I've been here before, and then constraints on the map were added on top of each other to be able to create the nice corridor looking hallway that you see in this image right here. And now I can show you all a demo of the robot using RTAB map to build a map of its local environment, which in this case happens to be my workspace. Now you will see once I play this video that the robot is going to be able to build a 3D point cloud of its environment while simultaneously building an occupancy grid, or in simpler terms, a map of its environment using the LiDAR sensor attached to it. This LiDAR sensor is essentially going to be able to detect whether or not there's obstacles within its path, or if there's no obstacles, which you'll be able to see momentarily. As you can see, it's already basically started the map building process at launch, and at this point the map is already basically put together for the most part, at least in terms of the 2D occupancy grid. You can also notice that fusing additional odometry from the camera, is known as visual odometry. It's being produced from RTAB map, which is being fused within the extended common filter to produce a better odometry estimation during mapping. And now I can show you all the finished product of the robot's mapping process as it was going through my workspace. And you can see that during the mapping process, it was able to pick up several key features that were able to be added to the 3D point cloud map. A few of them being this desk slash table that you also can see right here. My work table can also be spotted around this area, along with some other chairs, a desk, a couch, or at least the front of the couch is about right here. And if you pay close enough attention, you can also see my legs right around there. And I say all this is just to basically say that the RTAB map SLAM algorithm from the cameras is actually able to pick up most things, distinguishable features pretty accurately over time. So at this point in time, we really have everything that we need in order for the robot to be able to achieve autonomous navigation. However, we can make its job easier by providing it a pre-built map beforehand so that the robot has knowledge of all obstacles within this way, along with being able to produce long-term paths to whatever goal point we want to get the robot to within the map. But one question remains: how exactly do we localize the robot in the map? And by localize, I essentially mean determine where the robot is in the map at any given point in time. And while we can argue that the odometry estimation can, be a good buffer for that, we can also add another algorithm that also further robust the result of localizing within the map, which is known as the adaptive Monte Carlo localization algorithm. And basically, this algorithm is a particle filter, which basically sends out a bunch of uh, guesses of where the robot may be, and that's essentially what you see in this image right here. This is a map, the pre-built map of my workspace, and in the middle you see my robot here with a bunch of green spots all around it, and these green spots essentially represent guesses of where the robot could be, at that point in time. And over time, as the robot moves around, what you're going to see is that uh, the green dots are going to kind of converge. It's going to get smaller and smaller to a point where you're going to see that the localization algorithm is essentially going to be able to converge on where the actual location of the robot is. And now I can show you all a demo of the robot utilizing the adaptive Monte Carlo localization algorithm to localize itself within a pre-built two-dimensional map. And in this case, the two-dimensional map that I built is of my apartment that I'm currently staying in. And you can see right here that there's a bunch of green dots around the estimated location of the robot. And you'll see that over time, the green dots will get smaller and smaller, at least around the location of where it thinks the robot is located at. And you'll see exactly what I'm talking about momentarily. As you can see, the green dots are getting smaller and smaller, like converging into one location. Now, when it turns, it does spread out a little bit, and that is something that I am currently trying to work on. But overall, you can still see that it's still smaller than where it started out at. So now we have finally moved on to the point where we can talk about the implementation of the ROS Navigation Stack, and this is the third and final required step for the robot to be able to achieve autonomous navigation. And the algorithm that's within the ROS Navigation Stack must be able to generate motion paths that can take the robot to its target pose, all while avoiding obstacles, and also be able to send the robot velocity commands that guide the robot to follow the path that was generated previously. Thankfully, ROS also provides a standard algorithm that accomplishes all of this through the use of the move base node. Now, this move base node can be seen within this snippet of code that I've left here within this launch file. And as you can see, there are multiple different parameters that you have to tune in order for the move base to perform optimally. And I will talk about each parameter in the subsequent slides. So now we can talk about the first integral part of the move base node, which is using the local and global cost maps. And move base uses the cost maps primarily for obstacle avoidance by inflating regions of the robot's potential path trajectories to associate high cost with regions where obstacles are present and low cost with regions that are a free space. Basically, what you can pull from this is that the move base node produces a path, a trajectory from the robot's initial point to the goal point. And what it's trying to do is minimize the cost of the path that it generates. So paths that are closer to obstacles, they're going to have higher costs, which means that you have a higher likelihood of crashing into something. So essentially, it's minimizing the cost to produce the most obstacle-free path. And the way that these two cost maps differ is that the local cost map is a cost map that surrounds the robot in itself and it follows the robot as it's moving around, and it detects and inflates all obstacles within it and marks them on the map. A global cost map is one that stores and inflates all obstacle data from the pre-saved map if I am using one, which in this case I am using a pre-saved map, along with any new obstacles that are formed from the local cost map. So the global cost map, you can essentially think of it possessing all of the obstacle data from the local cost map, along with any other data that may obstacle data that may be there from uh, pre-state map or any other excursion. So here I wanted to give you all an illustrative example of the global and local cost maps in action. And what we can see here is that this is a simulation of the Turtlebot that is utilizing both a local and global cost map. So this square that's around this robot right here, this basically represents the local cost map, and what it's doing is detecting all obstacles within the robot's uh, vicinity, and it's marking them and inflating them with this red region, and essentially that's where the inflation comes into place. And then within the global cost map, it's also storing in all of this obstacle data, like from this local cost map, while also having knowledge of the other obstacles within the map. So, for example, we see these inflated regions around these walls, amongst other parts that aren't covered by the local cost map currently. And so, progressing from our conversation about the local and global cost maps, we can now talk about the global path planner, which its purpose is to produce an obstacle-free trajectory from the robot's initial pose to a target pose. And we see this image below right here, where we have a robot that starts off in initial pose right here, and we want it to get to a target pose that is positioned right here. And essentially what the global path planner is going to be able to do is produce a path, which is the green line, from the starting position to this target position that the robot will use to get to the target position. And in future studies, I'm going to be able to implement two different global path planners, which contain A star along with Dijkstra's algorithm, to be able to test the performance metrics to see how well they perform over time. The reason that I wasn't able to do that in this study is mainly because of the technical limitations of the robot currently. So moving on, now that we have been able to talk about the global path planner, we can now talk about the local motion planner, and this purpose is to send velocity commands to the robot's motors in order to guide the robot through the obstacle-free trajectory produced by the global planner, while also avoiding any new obstacles that may appear on the way. The local planner that was utilized by the robot in the study was the local planner plugin that MovieBase uses by default, the trajectory planner ROS. And what we see below is actually the same 2D occupancy grid of my workspace, but it also has all of the obstacles that were spotted within the map inflated. So you see all of these inflated spots where the obstacles once were. They're now inflated so that the robot knows, okay, I need to avoid these obstacles as much as possible. And actually, this picture was taken as the robot was trying to attempt to complete a navigation task. And we see that I guided the robot to go to this position. It starts off here, and this red line essentially represents the global motion planner, basically the line that it was able to produce that's obstacle free. And then there's this yellow line right here that's very close to the robot. It's the local motion planner. And basically what that represents is the velocity commands that are being sent to the robot, the trajectory that the robot needs to follow in order for it to be able to follow the red line essentially. So now we have finally made it to the moment of truth where I can show you all the robot performing autonomous navigation within a static 2D environment. In this case, I decided to use my apartment for the autonomous navigation task, and we see that all the obstacles within the apartment are all inflated like I showed you in the previous slide. And now I'm going to be sending the robot periodic navigation commands that it's going to try its best to follow through this navigation task. And you all will see exactly what I'm talking about in a second. You can see that I'm using purple arrows to tell it where to essentially follow. And you're seeing that it's trying its best to upkeep those trajectories. And I'm about to choose another one, and now it's following. See how it avoided the obstacles right there and still able to get to the goal position? That's essentially what the autonomous navigation is capable of. However, we see that it wasn't able to fully follow the trajectories that were being produced, mainly because the motor controller on board the robot isn't as strong as it could be. So that is definitely a area that I could improve on moving forward. And this guides me to my final slide, which talks about the current limitations of the robot along with potential future works. So I've touched on a few limitations of the robot so far, but we can understand that while the robot can accomplish navigation at an adequate capacity, there are a few modifications that can be added to improve the performance even further. One of those being improved wheel encoders that will be able to track linear and angular velocity a lot more accurately. Currently, the wheel encoders that are of use, while they can track it moderately well, there's definitely room for improvement in that regard. There's also the covariance matrices that are within the EKF or extended common filter localization node that the robot is using for odometry estimation that I could definitely tune in order for it to have quicker and more accurate convergence rates. I could also implement, and I've mentioned this before, a more reliable feedback controller than what is currently in use. Currently, the controller that I have the robot employing, it has a pretty slow transient along with, not great steady state error response. So using a better version of that control that I'm currently using, or even implementing some form of a PID, would be optimal in order for the robot to be able to achieve the autonomous navigation tasks that I would like it to be able to accomplish. Also, for future works, once the odometry estimation, localization, and control implementations above all improved, this robotic platform can be utilized in a wide range of different potential research routes. Some of them including the performance analysis of different ROS global path planners, and I touched on this a little bit before. I could compare the performance metrics of A-star and Dijkstra's algorithm in order to be able to determine which one is more optimal in certain situations. I could also consider implementing some type of advanced control paradigm. So we could think about model predictive control, reinforcement learning, anything of that nature. All of it is within realm of possibilities with this robot. And because there is a depth camera attached to the robot as well, we can also consider some type of vision-based autonomous navigation algorithm implementation as well. And that concludes my talk. I just want to thank you all for taking the time to listen. And if you have any questions with regards to the implementation of the ROS Navigation Stack, or with anything in regards to the project in general, do not hesitate to reach out. Thank you again. And for those who are wondering, this is my reference list right here.